Landing distance definition. Required landing distance. The RLD is the factored certified landing distance based on maximum manual braking initiated immediately after main gear touchdown. Prompt selection of max reverse thrust, maintained to 70 knots, and idle thrust to full stop when reverse thrust is taken into account. Anti-skid system and all ground spoilers operative. The regulatory dispatch factor. Note: the RLD calculation considers the effect of the MEL/CDL items that affect the landing performance. In-flight landing distance. The in-flight landing distance calculation assumes an airborne phase of 7 seconds from threshold to touchdown. In the case of manual braking, maximum manual braking initiated immediately after main gear touchdown. In the case of auto brake, normal system delays in braking activation. Anti-skid system and all ground spoilers operative. Prompt selection of max reverse thrust, maintained to 70 knots, and idle thrust to full stop when reverse thrust is taken into account. Note: the in-flight landing distance calculation considers the effect of the inoperative system following an MEL/CDL dispatch that affects the landing performance, an in-flight failure ECAM alert that affects the landing performance. Factored in-flight landing distance. The definition of the in-flight landing distance does not include any margin. The in-flight landing distance is a realistic distance achievable in nominal conditions, i.e. the actual conditions during the landing are those used for the computation. It is recommended to apply an appropriate margin to the in-flight landing distance either determined with or without failure in order to cover the variability in flying techniques, e.g. flare execution, delay in application of the deceleration means, unexpected conditions at landing, e.g. real runway friction versus reporting, turbulence, crosswind. The FLD is defined as the in-flight landing distance multiplied by a factor, or the in-flight landing distance plus an increment. It is the airline's responsibility to define the margins and their applicability to apply on top of the in-flight landing distance. The recommended margin is a factor of 1.15 on the in-flight landing distance. In an emergency situation, the flight crew may decide to disregard this margin. Operations on contaminated airports. If the ground surfaces are not contaminated but the weather corresponds to icing conditions with falling rain, slush or snow, anticipate a probable resulting runway surfaces contamination. There is a low probability of fluid ingestion by the engines which should anyway not degrade the safety. The risk of ingestion is independent of the depth of the contaminant. Undue alerts. On the ground with contaminated surfaces or de-icing fluid on radio altimeter antennas, the radio altimeters may indicate some erroneous values or no values. If the PFD displays erroneous radio altimeter values, the flight crew can disregard the triggered auto callouts and/or the GPWS, eGPWS alerts. Note: undue GPWS, eGPWS alerts may trigger at the apron, during taxi, takeoff and landing runs. If the PFD does not display any radio altimeter values on both sides, the flight crew can disregard the following alerts: all engines failure, anti-ice captain TAT or anti-ice FO TAT, landing gear shock absorber fault, stall warning, engine reverse unlocked, engine reverse set, nav TCAS standby, brakes parking brake on. The PFD recovers the radio altimeter indication in the following cases: the aircraft is on a non-contaminated surface, or The radio altimeter antennas are no longer covered by any fluids, de-icing fluid or water. The flight crew must check that the radio altimeter values are indicated on the PFD before entering the runway. Contaminated runway. A runway is contaminated when a significant portion of its surface is covered with a layer of fluid contaminant not considered as thin, a hard contaminant. In terms of performance, a contaminated runway is a runway covered by a fluid contaminant with a depth of more than 3 mm. The fluid contaminant can be either dry snow, wet snow, standing water, slush. Fluid contaminants reduce friction forces and cause precipitation drag, hydroplaning. In terms of performance, a contaminated runway is a runway covered by a hard contaminant that can be either compacted snow, ice cold and dry, wet ice. Hard contaminants only reduce friction forces. Flex takeoff is not permitted on contaminated runways. Dispatch from or to a runway covered with wet ice is not permitted, unless a specific method for performance assessment has been established by the operator. Computation principles. TOD and profile computation. The FMGS calculates the top of descent point backwards from a position 1000 feet on the final approach with speed at VAP. It takes into account any descent speed and altitude constraints and assumes managed speed is used. The first segment of the descent will always be idle segment until the first altitude constraint is reached. Subsequent segments will be geometric, i.e. the descent will be flown at a specific angle, taking into account any subsequent constraints. If the star includes a holding pattern, it is not considered for top of descent or fuel computation. The top of descent is displayed on the ND track as a white symbol. The idle segment assumes a given managed speed flown with idle thrust plus a small amount of thrust. This gives some flexibility to keep the aircraft on the descent path if engine anti-ice is used or if winds vary. During idle segment, the auto-thrust commands thrust idle or depending on FMGS standard, Mach, speed. During geometric segment, the auto-thrust commands Mach, speed. With descent profile optimization option, the idle segment assumes a given managed speed flown at idle thrust. This gives less flexibility to keep the aircraft on the descent path if engine anti-ice is used or if winds vary. In case of use of engine anti-ice or increased tailwind, the use of speed brakes may be required to go back on the descent path. Managed descent speed profile. The managed speed is equal to the econ speed, which may have been modified by the crew on the perf descent page before entering descent phase or during descent phase depending on FMGS standard, or the speed constraint or limit when applicable. Holding speed and configuration. Whenever holding is anticipated, it is preferable to maintain cruise level and reduce speed to green dot, with ATC clearance, to minimize the holding requirement. As a rule of thumb, a Mach 0.05 decrease during 1 hour equates to 4-minute hold. However, other operational constraints might make this option inappropriate. A holding pattern can be inserted at any point in the flight plan or may be included as part of the star. In either case, the holding pattern can be modified by the crew. If a hold is to be flown, provided nav mode is engaged and the speed is managed, an automatic speed reduction will occur to achieve the hold speed when entering the holding pattern. The default hold speed is the lowest of the following. Maximum endurance speed. ICAO limit holding speed. Speed constraint. When no specific speed limit applies, the default hold speed is the maximum endurance speed, which is approximately equal to green dot and provides the lowest hourly fuel consumption. If the maximum endurance speed is greater than the ICAO or state maximum holding speed, the crew should select flap 1 below 20,000 feet and fly S speed. Fuel consumption will be increased when holding in anything other than clean configuration and maximum endurance speed. Discontinued approach. The discontinued approach is an alternative technique to the go-around procedure to interrupt an approach when the aircraft is at or above the selected FCU altitude. Contrary to the go-around procedure, the discontinued approach technique does not require the flight crew to set the thrust levers to toga detent. The flight crew should initiate the discontinued approach technique with the callout, "Cancel approach." The first action of the flight crew is to disengage and disarm any AP/FD approach mode, by pressing on the approach push button or lock push button. If at or above the FCU altitude, announce "Cancel approach." To disarm any AP/FD approach mode, press approach or lock. Select lateral mode as required nav or heading mode. Select vertical mode as required level off or adjust VS. Select speed and adjust. Go around near the ground. The PF must not initiate a go-around after the selection of the thrust reversers. If the PF initiates a go-around, the flight crew must complete the go-around maneuver. If the flight crew performs a go-around near the ground, they should take into account the following. The PF should avoid excessive rotation rate, in order to prevent a tail strike. If the engines are at idle when the go-around is initiated, the engines can take a few seconds for the engines to spool up and the flight crew may need to maintain the pitch until the aircraft speed increases up to VAPP. A temporary landing gear contact with the runway is acceptable. Only when the aircraft is safely established in the go-around, the flight crew retracts flaps one step and the landing gear. Parking brake. Check the ACU press indicator. The ACU press indication must be in the green band. In case of low accumulator pressure, chocks are required before engine 1 shutdown. Set parking brake handle on. If the temperature of one brake is above 500 degrees Celsius or above 350 degrees Celsius with the brake fans on, avoid applying the parking brake, unless operationally necessary. Then check brakes press indicator. Caution. Keep the brake pedals pressed until both needles of the brake's pressure indicator are above the green area, to avoid inadvertent movement of the aircraft. Engine tailpipe fire. An engine tailpipe fire can only occur at engine start or at engine shutdown. It is the result of an excess of fuel in the combustion chamber, in the turbine or in the exhaust nozzle, that ignites. A tailpipe fire is an internal fire in the engine, compared with an engine fire that occurs outside the engine core and gas path. No critical areas are affected in the engine in the case of a tailpipe fire. However, it can have an effect on the aircraft, e.g. damage the flaps. The correct method to manage an engine tailpipe fire is to stop the fuel flow, and to ventilate the engine. In the case of a tailpipe fire, there is no cockpit alert. The only indication can be an increasing EGT due to the fire in the turbine. Therefore, most of the time, the ground crew, cabin crew, or ATC visually detect the tailpipe fire. In the case of a tailpipe fire, the flight crew must apply the QRH-ENG tailpipe fire procedure, which requires the flight crew to shut down the engine, in order to stop the fuel flow. dry crank the engine, to remove the remaining fuel. The flight crew should not use the engine fire push button. This cuts off the electrical supply of the FADEC, and stops the dry crank sequence performed by the FADEC. The flight crew should not use the fire extinguisher, as it does not extinguish an internal engine fire. As a first priority, the fuel flow must be stopped, and the engine must be ventilated. If the tailpipe fire procedure does not stop the fire, or if bleed air is not easily available, the ground crew can use a ground fire extinguisher as a last option. Ground fire extinguishing agent can cause serious corrosive damage to the engine and requires a maintenance action on the engine. Takeoff configuration. As a general rule, config 1+F gives better performance on long runways, better climb gradient, whereas config 3 gives better performance on short runways, shorter takeoff distances. Sometimes, other parameters, such as obstacles, can interfere. In this case, a compromise between climb and runway performance is requested, making config 2 the optimum configuration for takeoff. Environmental takeoff conditions may also impact the choice of the takeoff configuration. Flexible takeoff is the recommended method for takeoff at reduced thrust on dry and wet runways. The highest flexible temperature T-flex extends engine life and saves maintenance costs. However, if a high T-flex is reduced by a few degrees only, the engines are not significantly affected. The highest T-flex will usually be obtained at the lowest flap setting. However, a higher flaps setting provides a lower decision speed V1 and more comfort. To extend engine life and to save maintenance costs, the use of flaps setting that provides the highest T-flex is recommended. However, when the difference in terms of T-flex between two configurations is low, the highest of both takeoff configurations is preferable. No flight director takeoff. If a takeoff is initiated without FD, the system responds as follows. There are no FD bars. There is no arming. There is no guidance available. The target speed on the PFD is that selected on the FCU or is defaulted to 100 knots. Setting the thrust levers to the climb detent does not activate auto thrust. Note: do not engage the auto thrust prior to selecting a target speed on the FCU. Procedure. Establish initial climb of 15 degrees. When reaching the thrust reduction altitude, select a climb speed. Set the thrust levers to climb detent. Activate the auto thrust. Turn on the FD's basic modes. Engage. Select appropriate mode. Failure of both FDs after the start of takeoff. The FD bars disappear. The FCU window displays the target speed, which synchronizes on V2, or the current speed if it is higher. The auto thrust remains armed. At thrust reduction altitude, LEVRR climb flashes. If the pilot set the thrust levers to the climb detent, the auto thrust becomes active in selected speed mode. No FDs selected. If the current speed is greater than the target speed, the thrust decreases. At acceleration altitude, the target speed does not change, since it is selected. Takeoff with no V2 entry. If V2 is not inserted, the Speed Reference System (SRS) will not engage for takeoff. 5 seconds after liftoff, VS mode will engage. When VS engages, the current airspeed becomes the FCU target speed. To regain a normal speed target, the pilot must select the appropriate climb speed on the FCU and pull out the knob. At acceleration, Alt. Push the auto thrust push button on the FCU. Set the thrust levers to climb detent. Push in the SPD selector knob to get a managed target speed. Speed decay during cruise. Factors that cause a speed decay during cruise. On aircraft with no failure, and the 8 THR engaged or the max CLB thrust applied in manual mode, a continuous speed decay during cruise phase may be due to a large and continuous increase in tailwind or decrease in headwind, in addition to an increase in the OAT, that results in a decrease of the rec max flight level, or a large downdraft, when the flight crew flies parallel and downwind in a mountainous area, due to orographic waves. The downdraft may have a negative vertical speed of more than 500 feet per minute. Therefore, if the aircraft is in a downdraft, the flight crew must climb in order to maintain altitude, and the pitch angle and the thrust value increase. Without sufficient thrust margin, the flight crew may notice that aircraft speed decays, but the rec max flight level is not modified. Thrust margin and external parameters. The flight crew must be aware that at high altitude, the thrust margin difference between the thrust in use and the maximum available thrust is limited. The maximum available thrust decreases when there is an increase in altitude and/or outside temperature. In some conditions, MCT may be the maximum available thrust. In such a situation, it is useless to put the thrust levers in the toga detent to try to increase the thrust. The rec max flight level indicated in the prog page of the MCDU decreases when the OAT increases. The nearer the aircraft is to the rec max flight level, the smaller the thrust margin. Green dot speed as a reference. The optimum lift, drag speed is the green dot speed. The green dot speed uses the lowest quantity of thrust necessary to maintain the required, desired altitude. When the aircraft speed is below green dot speed, any decrease in speed requires an increase in thrust in order to maintain the required, desired altitude. Therefore, if aircraft speed is below green dot speed and continues to decrease, even with the maximum available thrust in use, if the flight crew maintains the current altitude, the angle of attack will further increase. Operational recommendation. The nearer the aircraft is to the rec max flight level, the smaller is the thrust margin that the flight crew has to manage a speed decay during cruise. If the aircraft speed goes below green dot speed, with the maximum available thrust in use, the only way for the flight crew to avoid an increase in the angle of attack is to descend. Note: with the autothrust on, the selection of the open descend mode reduces the thrust to idle, and therefore increases the time to recover the energy. As a result, the flight crew can recover normal aircraft speed and the normal thrust margin. Fuel temperature. Fuel freeze refers to the formation of wax crystals suspended in the fuel, which can accumulate when fuel temperature is below the freeze point -47 degrees Celsius for Jet A1 and can prevent proper fuel feed to the engines. During normal operations, fuel temperature rarely decreases to the point that it becomes limiting. However, extended cruise operations increase the potential for fuel temperatures to reach the freeze point. Fuel temperature will slowly reduce towards TAT. The rate of cooling of fuel can be expected to be in the order of 3 degrees Celsius per hour with a maximum of 12 degrees Celsius per hour in the most extreme conditions. If fuel temperature approaches the minimum allowed, the ECAM outputs a caution. Consideration should be given to achieving a higher TAT. Descending or diverting to a warmer air mass may be considered. Below the tropopause, a 4,000 feet descent gives a 7 degrees Celsius increase in TAT. In severe cases, a descent to as low as 25,000 feet may be required. Increasing Mach number will also increase TAT. An increase of Mach 0.01 produces approximately 0.7 degrees Celsius increase in TAT. In either case, up to 1 hour may be required for fuel temperature to stabilize. The crew should consider the fuel penalty associated with either of these actions. Low energy oral alert. An oral low energy speed alert, repeated every 5 seconds, warns the flight crew that the aircraft's energy level is going below a threshold under which the flight crew has to increase thrust, in order to regain a positive flight path angle through pitch control. It is available in configuration 2, 3, and full. The FAC computes the energy level with the following inputs: aircraft configuration, horizontal deceleration rate, flight path angle. The oral alert is inhibited when toga is selected, or below 100 feet RA, or above 2000 feet RA, or alpha floor or the ground proximity warning system alert is triggered, or in alternate or direct law, or if both radio altimeters fail. During deceleration, the low energy oral alert is triggered before alpha floor unless alpha floor is triggered by stick deflection. The amount of time between the two alerts depends on the deceleration rate. Low energy recovery. Increase the thrust and/or adjust the pitch depending on the situation, until the oral alert stops. Engine vibrations. Engine vibrations are usually caused by an imbalance of the engine that can be due to many reasons, such as a deformation of one or several blades due to foreign object damage, or a bird strike, a rupture or loss of one or several blades, an internal engine failure, a fan icing. High engine vibration alone does not require an engine in-flight shutdown. If the engine needs to be shut down, other symptoms and certainly an ECAM alert will warn the flight crew and request them to shut down the engine. A high N1 vibration level may be accompanied by perceivable airframe vibrations. When the vibration level exceeds a certain threshold, an ECAM alert triggers and an ECAM advisory function automatically highlights the affected parameter. The ECAM alert guides the flight crew toward the QRH, high engine vibration procedure. In the case of high engine vibrations, the flight crew first checks the engine parameters and cross-checks them with the other engine. The flight crew identifies if there are engine vibrations only, or if there is another problem on the engine for which the flight crew may expect an ECAM alert. Then the flight crew determines if icing is suspected or not. The flight crew should suspect icing if N1 vibrations occur without variation on other engine parameters. If the flight crew notices unexpected behavior on other engine parameters, the flight crew should consider that icing is not suspected. These checks take into account the cases of engine problems in icing conditions, and also the cases of vibrations due to icing, out of standard icing conditions. If the flight crew suspects icing, and if flight conditions permit, the flight crew should shed the ice with the following procedure. The flight crew disconnects the auto thrust. The flight crew performs several large thrust variations from idle to a thrust compatible with the flight phase. It may be necessary to perform several engine run-ups, decrease and then increase of thrust to fully shed the ice. If the flight crew does not suspect icing, and if flight conditions permit, the flight crew reduces thrust to make the vibrations decrease, and stay below the ECAM alert and ECAM advisory threshold. If the vibrations do not decrease, there may be another problem with the engine. The flight crew should expect an ECAM alert that will provide guidance on the actions to perform. Finally, during the taxi-in phase, the flight crew may consider to shut down the engine if the flight crew experienced vibrations in flight, or if the flight crew experiences vibrations during taxi. On ground, the flight crew should consider engine shutdown in order to avoid increased damage to the engine. Engine out max altitude. The FMS engine out maximum altitude is a precomputed value, function of the aircraft gross weight and DESA, displayed on all the perf pages if one engine is inoperative. Engine out maximum respects the following criteria. It can be flown with long-range cruise speed. It can be held in level flight with the operating engine at maximum continuous thrust rating. The failed engine in windmilling. Anti-ice off. It can be reached before buffeting with a margin of 0.3 g. It is less than the maximum certified altitude.